So I've got a really big topic to try and cover and fill in Julia's lovely talk with the right lead-in to the development of non-lethal science. So I'm aware of my timeline, so I'll try and go slowly for the translators, but I do have to go reasonably quickly through the slides. Where are we? So I'm going to talk a little bit about the context of where a lot of the techniques that we're going to hear about in great detail from many of the sort of world-leading experts in those fields today, the context of where that science arose, a little bit about what drove the need for that type of science. I'm then going to talk to you a bit about the Southern Ocean Research Partnership, but not much. I'm going to just cover that fairly quickly. I hope you know about it. I hope you'll learn more about it at the meeting here. And of course, this event itself is one of the major projects of the Southern Ocean Research Partnership that grew out of the IWC. And I'm going to leave with the last couple of slides. I hope I do have time to spend a bit of time on, because I want to sort of put a challenge out about where I think we ought to be taking cetacean science in general. So here's I guess a fairly simple timeline on the evolution of the different types of sciences, going back to the mid of the last century and roughly where we're at now. Throughout that period of time, we have had and continue to have the important aspect of museum science, the taxonomic collections that are valuable when they're collected and become increasingly valuable as time goes on, massively important reference collections. We had the commercial whaling science, if you like, the science that was done around commercial whaling. We know the management story, we've heard about that, but there was some science done back then to try and understand the animals that were being taken, that went through the era of that large industrial whaling. And then post-moratorium whaling science, if you like, the work that the IWC has been doing more recently, and in particular, I guess, the science side of that has been led by the development of methods to derive catch limits for commercial whaling within the IWC. So that all sits within the whaling era, and I'm not going to touch on that at all today, of course. In the single species science, we had areas, I'm sure lots of you can argue about exactly where I start these timelines, but in general terms, where the sort of the population monitoring of recovering populations came. I'm going to talk a bit more about that. The life history work, followed by more behavioural and social structure studies, and more recently studies on disease of free-ranging animals. And we've had a whole lot of science that has emerged about trying to manage threats, understand the threats of fisheries, operational interactions, entanglements, and later on the sort of trophic interactions, competition for resources and so forth, whale watching science, and now ocean noise and the effects on animals in the ocean. And we're going to hear from Lisa after this talk about the ecosystem science, much of which as well relates to aspects of changing ecosystems and changing climate. So effectively moving through from the lethal aspect to the part I'm going to talk about, the various aspects of non-lethal science. So from the origins of our science, the bloody past, we've just heard all about. The post-World War II established the foundations of what we know today. So this really was on and so quite a few of the older folk at the IWC were the biologists who were on the flensing decks with their knives and buckets. And actually a lot of that descriptive biology is is fundamental to what we know today on some of those species. The discovery marks that were fired into animals, that we'll hear a bit more about as well, I think, showed us some evidence of movements of animals where they had these marks fired into them and where they were ultimately killed. And sighting surveys and catch statistics provide a whole lot of information about the demise, effectively, of those populations. And it's fair to say that at the time that was the state of the art of the science. It was how the science was conducted at that time. We then have the collapse of populations, the moratorium, comprehensive assessments. So we had the cascade of population collapses through the 20th century, then staggered protection of the different populations, very late, tiny populations remaining, and finally the moratorium in '86. The comprehensive assessment in the IWC framework, which was established by the IWC effectively as a tool to really measure the effects of the moratorium. So these were assessments of populations. It's changed now. The comprehensive assessments are much more about understanding the overall status of populations. But at that time there was a major need for real advancements in non-lethal studies of those depleted whale populations. So the pioneers of this science, with little encouragement early on, this is difficult work and it's expensive to get out there and work on whales. They're really rotten research models. You can't play with them like you can Drosophila or lots of nice little laboratory animals, so the science is tough. So the people were highly imaginative who led that. There was a lot focusing on IWC needs, but a lot focusing on the biology and the much broader needs for the cetacean science. And of course, it really did pick up initially on those more accessible nearshore species. And a lot of the long-term surveys were started there, and the sort of starts of photo identification, and we're going to hear a lot more about this type of work. So that whale recovery science, the counters and the camera, the surveys, people like Mike Node in the audience will recognise this graph on the right there of population, long-term monitoring of these populations recovering, and this is a East Australian case, the central one, whalers turned whale counters in the middle there, some work that Simon Childerhouse led with others in Cook Strait, monitoring the recovery of the humpback whales around New Zealand. And of course all of the advances that have been made through photo identification and resites of the animals, in this case showing some results from movements of known humpback whales through the Oceania region. The next major era was the technological era, the rapid expansion of non-lethal research opportunities, and it was driven by a whole lot of, we could mix these categories a bit, but this is how I'm structuring my talk, a whole lot of areas around whales and sound, electronics and biotelemetry, molecular science, the whole range of statistics, mathematics and computer power that led our ability to do this work, and remote sensing. So I'll be covering some of these topics now. So whales and sound, I'm not going to touch on this. Kate Stafford will be talking about this later on today, but it was the famous story of being able to track blue whales. The Navy found they could hear these whales, they knew all about them, and I'm sure Kate will touch on some of that story later, but it was really the recognition that whales make these unique sounds that can be heard over huge distances. And I'll stick my neck out here, and the acousticians can take me to task, but I'll do a list of what I think really are the realities and the promise of acoustics at the moment. So from the acoustic signals we can detect, track and locate individual animals, and in particular rare species such as North Atlantic right whales, and as one of the big SORP projects, this is a major part of working with Antarctic blue whales. We can infer population structure from different sound types. We can track the relative population trends through changes in acoustic densities over long periods of time with more acoustic arrays and more acoustic recorders. Perhaps, one day, maybe, we can estimate relative abundance. We can measure patterns of habitat use by leaving moorings there and looking at how the animals that are vocalising coming in and out. We can infer behavioural states. We get insights into foraging ecology through sound, especially on odontocetes. We now know more about how rare beaked whales forage than a lot of common species through the very clever use of acoustics. And we can measure other elements of the environment. I'll touch on electronics and telemetry now. So this was led really through the miniaturization and enhanced data storage and transfer in data logging and telemetry. And the techniques really were developed on other marine mammals that are much more tractable, and then applied to whales later on. And this has been much of the story in a lot of the whale tools applied in biotelemetry, that they're far more evolved in animals that you can restrain and recapture and deal with than these bloody awkward large animals that are difficult to deal with at sea. But we've learned a huge amount through this, and a whale's eye view of the world. And they're tracked at the scale of metres right up to whole of ocean basins. So some work that Ari Friedlander will talk about later today of deploying these D-tags on whales, and where you get incredible structure through the water column in 4 dimensions with time of the animal's movement, through to great ocean basin transits that Alex Sabini will talk to us later on about as well. Oh, sorry, let me go back to that and see if that can work. Oops. Do I go back? Back to black. Here we go. So just a simple example of some humpback whales, ice movement down here with tracks, and this sort of insights from these tags are simply impossible to gain in any other sort of cross-sectional survey technique. And if you watch some of the tags that lasted longer, you can get insights into the way they interact with that changing ice zone over a period of around about 5 or 6 months. There's the last animal left down there with a tag working and being pushed out by the ice, interacting with that ice edge, and starting to come home, and the tag failed. But these are insights that were simply not available to us with any other technologies. So similarly, the realities and promise of biologging are these extraordinary insights into the habitat used in 4 dimensions across multiple scales. We're really just starting to take advantage of that. Insights into foraging ecology, behavioural insights, interactions with the physical environment. So just quite extraordinary. So moving now on to molecular science, and we'll be hearing more about this afternoon. I will in a minute. Thank you, Barbara. So from a single biopsy taken from a whale, we collect a piece of tissue from which we can extract DNA. We can get an individual identification from that animal. We can learn about its relationships to other animals. We can even infer populations from where that came. And finally, from that, we can make some inference about there's a population trend of animals through whaling and then recovery. We can make inferences about how small that population became, and some of the work infers that we can also get inferences about what the original population abundance must have been before from the DNA. We can also now start to get some idea, some promise, this is in the future perhaps, on the age of animals from the DNA, and there are people working on that at the moment. And we can learn about the health status of those animals from those tissues. We can also collect feces and extract DNA from them and learn a lot more about what the whales are actually eating from the remnant prey DNA, and there'll be more about that in the workshop afterwards. But from that same biopsy sample, we can also collect some fatty acids that are in the blubber, and from the fatty acids we'll be learning more from Gino later on about how you can infer age from fatty acids. And you can also learn about what the animals are eating from the way they accumulate the fats that they eat from their prey. You can collect stable isotopes, learn about prey, and you can collect hormones and learn about the animal's reproductive status. So from a very small sample, we can now learn just an extraordinary amount of information, and that's becoming more and more by the day. I'm sure I haven't included everything there. Perhaps as important and not as spectacular as some of the other ones, but behind all of this is all of the statistical, mathematical, computer power that's made a whole lot of the work possible. So the population estimation work, the development of survey techniques and mark recapture studies. In many ways, we're leading the people involved in distance sampling in cetaceans, where it's so complex, are leading the field in many of the statistical modelling techniques that are used for surveys. And of course the data processing, data exploration and visualisation, just some extraordinary visualisation tools available to us now to look at the outputs from these tags that collect so much information and so much data, we can't deal with it normally. So, large integrated cetacean studies in the Southern Ocean, bringing us down to here. We were going to have a separate talk on the International Decade of Cetacean Research and the Southern Ocean Whale and Environment Research, which is the IWC and Japan-supported sighting surveys that ran for about 3 decades around Antarctica, provided an incredible amount of information and a huge legacy of information, many publications from the sightings records there, which were focused principally on estimating minke whale abundance, which we still can't yet get to an agreed point on in the IWC, but we're closing on it, but also blue whale abundance and a whole lot of other things. But in actual fact, it's almost certain that'll never be repeated. No country has the resources now to put vessels down there for research which do sighting surveys every year, 2-3 ships at a year. So we need to work on the Southern Ocean in this area in a more clever manner than just straight out sighting surveys. So this is where the research partnership has come in. It has to be clever in the way we deploy these tools against questions that are agreed within the IWC, and that's what we've been doing, and I'll be touching on that briefly now. So I just want to remind people about why the Southern Ocean is important. The Southern Ocean is the ocean mass that links all of the great ocean basins, with both through the currents, the deep water and the upper level currents. This links all of the oceans. What goes on in the Southern Ocean drives global climate. The changes driven by climate in the Southern Ocean are going to be profound, and those consequences are going to cascade through, up and down the water column. And so it's a very important area for us to understand what's going on, and in this context, the whales. So the partnership is, there's now over 10 countries involved in 4 key research projects. I'm not going to talk about this workshop, that's a separate one, that's a 5th, using multiple methods. We have a large one that's looking at breeding to feeding, habitat utilisation by humpback whales, and there's a few key partners involved in that work. There's a particular focus at the moment on Oceania, but that's going to expand out into the Atlantic region as well, and a meeting on Friday to further coordinate under that project. Each of these projects have project leaders. Niche partitioning between minke and humpback whales. This in particular is a collaboration. Ari Friedlander will be talking more about this, and we're involved in this work with high density D-tags, short-term D-tags, collecting these data. And a study led by Bob Pittman and others in the US, and involved with Christophe and others from France, are involved in a major study on the different ecotypes of the killer whales. And the final one is this very large study, which would be a whole talk in itself. I'm not going to spend any time on this, but the Antarctic Blue Whale Project, which is going to be a multi-year, multi-methods approach using ships from all around Antarctica in trying to understand where blue whales are at. We know that their population is increasing ever so slowly, but they're way down at less than about 2% of the numbers that were once there. And this is an effort now to use all of these best and most appropriate tools to determine what's going on with that population. So my take-home message is, before I get onto the challenge, is that the current research tools allow cetaceans to be considered along with other southern ocean predators. If you go into most of these large, broader ecosystem and ocean basin scale science fora, and you look at the outputs from them, you'll see predators really well represented in there. The seals and the penguins, the flighted seabirds, and whales are very often, especially in the southern hemisphere, absolutely distinct by their absence in there. We tend to do the whale science in isolation and don't take it into those arenas. So now I think the tools are well and truly there, and increasingly so, that we can bring them in with the other southern ocean predators. SORP offers a good framework to do that, to conduct this large scale work, and focus very much on the key priority and agreed questions. And it needs, this is the implementation stage. So I hunted around on the internet to look for one of those old signs about needing you. But this is the phase at which SORP will live or die, really. Everyone has through the IWC countries, been very supportive of the fact that this is a great idea and we should engage, but it's really now we need the countries to be writing up those applications that go in through their national polar programs and elsewhere to get shipping resources to deliver and against the various projects to show its success, so that it can go beyond the time frame that it's currently limited to. And this big point about the fact that the international cetacean science needs to engage beyond just the IWC. We need to link to large national polar programs. And that's a really key message in all of the countries. It's the polar programs through most of the countries that run the Antarctic research, that make the decisions on the deployment of Antarctic operational logistics, ships, planes, people. So we need to have much stronger linkages there and be making ourselves known and the science we do known through the Scientific Committee of Antarctic Research and through CAMELA and others. And we need to link into large multidisciplinary programs. I'll talk more about that in a second. And stress the importance of maintaining these targeted long-term monitoring projects. So my final slide is the challenge, and it's looking at cetaceans as sentinels of ecological and climate change. I believe cetaceans are unique in the fact that they really can provide a biological near-century signal of change in the Southern Ocean. It's unique because we can combine the catch data. So unlike many of the other species that were exploited heavily in the Southern Ocean, at least with whaling, and we've heard from Yulia about unreported whaling, but now we do have a reasonably comprehensive record of what was removed from the ocean nearly 100 years ago. And so we have a signal about what was down there. With the long-term data and looking at the population recoveries, combining those two things, and now with our new techniques, I believe we can provide a signal, a rare biological signal, from those oceans about scales of change. They're complicated. We have to disentangle changes in the system itself with the changes that are wrought demographically through recovery of different species, but that's really important. We must become part of these large multidisciplinary programs, and I've put two up there. The ICED program, integrating climate and ecosystem dynamics, and the Southern Ocean, I was actually meant to come up second, the Southern Ocean Observing System. SOOS was supposed to be the one down below, and then I'm too clever by half. I meant to have that second one, the Sentinel, coming in over the top of it. But the main point is there are a number of these large projects. Things like the Southern Ocean Observing System are very focused on collecting the physical data. They need a biological context coming into them. The ICE program are certainly extremely interested in seeing the whale component feed in as the biological elements into those. I did it the wrong way around. So there's the SOOS. I've already mentioned that one. The other part, the other final point, is that I think the other element that we can learn a lot from the physical scientists, and indeed now from the geneticists, is about the importance of open data. As we get our data, making it publicly available for others to use. The normal reaction of collecting your own data is to wait until you've fully analysed it and written it all up, and I think more and more of us are now learning that when you put it all out there, you still do that, but other people use it as well, and it gets out and it's much more widely used, and it's extremely efficient in the oceanographic world. It's their modus operandi, and it ought to be much more the way that we do our business as well. That's it. Thank you very much.